Hey everybody, I am normally Ken the Metal Professor. Today I'm Ken the Mick Foley Professor because it's Halloween weekend and in just a little while I'm off to do radio coverage of a local wrestling show. So I figured Halloween, let's do the thing. So I got my Mick Foley gear. If you don't know who Mick Foley is, don't worry about it. But yeah, Mr. Sacco here on the side. Yeah, okay, that's enough of Mr. Sacco. Anyway, so pardon the unusual outfit here. I guess that's the point of this introduction. So this is another entry in Recently on Math Reddit, where I've scoured some of the math subreddits for a few problems that give a little bit of something interesting that might be of wider interest. It's been a couple of days since they were posted and have received good answers for. So I figure it's okay to kind of talk through some of the results, which is normally not what you want to do for something that's just immediately been posted, right? You want people to think about these things, but it's been a while. So it's like going over a test once you get it back, I suppose. So the three problems I'm going to take a gander at here, one involves plotting polynomials, and one involves the use of some trig identities, and one involves finding a derivative that involves an inverse trig functions. And again, there's some bigger themes in these problems that are good just to review in a broad sense. So the first one came off of the pre-calculus subreddit, and the question was posed as find the roots and give their multiplicities for this particular polynomial, and what's the behavior of the graph at the roots. Does the graph actually cross the x-axis, or does it just come down and touch the axis, or go above and touch the axis, go up from underneath and touch the axis at those roots? So getting to the roots isn't bad. There is a term you can factor there, and then hopefully you can recognize that the remaining quadratic expression is a perfect square. So this function simplifies down pretty quick to x cubed times x minus 3 squared. So right away we can see there's a root at x equals 0 because of that term. Remember, a root is where the polynomial will take on a value of 0 when you plug that number in for x. So we plug in x equals 0, the function becomes 0. X equals 0 is a root. The multiplicity is how many times in the expression for the function that root appears. Since x cubed is technically x times x times x, right, has multiplicity 3. And then also there's a value x equals 3 that will make this 0, which will make the whole function 0. So x equals 3 is a root. And because this factored term right here is x minus 3 times x minus 3, that root makes an appearance twice, and so it has multiplicity 2. Okay, that's the basic stuff. So the next part of the question is, well, how does this graph behave in the vicinity of these roots, and how the graph interacts with the x-axis? So this is the interesting part of the problem, because I want to stress that you can think about these things without plotting a ton of points. And so I'm going to have a picture here. So remember, our function is x cubed times x minus 3 squared. And what I've done here is I've just drawn a number line and I've put markers in for x equals 0 and 3. And we're going to think about what this function does in between those markers. So to the left of 0, if I have a negative value for x, then x cubed is negative, but of course x minus 3 squared will become positive. And so what we're looking at there, let me make sure I have the, I just discovered how to use colors on my tablet, which is pretty exciting. So this function, when we plug in values to the left of 0, will have a negative number times a positive number, which means that overall that function is going to be a negative number. And that means that the graph is going to be down here below the axis. In between 0 and 3, this number will definitely be positive, and so will this. So that function will produce a positive times a positive, or positive overall, and then certainly greater than 3, this function will also be positive. And so that means that the graph is going to be above the axis between 0 and 3, and above the axis on the other side of 3. And so without plotting any specific points other than 0 and 3, we can at least get the trends, because we know the graph is going to be negative to the left of the origin and then positive, but then it has to come back down and hit this point, but then it has to stay positive after that point. And so you kind of already can get a sense of what the behavior of this graph looks like. Now, we don't exactly know where that peak is or how high that peak is, but just for trends, we've got it. We know where it actually crosses the axis, and we know where it just touches the axis. The reason you might want to get comfortable with something like this, drawing a number line, putting in some markers for some special values of x, especially if you're in pre-calc right now, is that when you get to Calc 1, you're going to do that a lot because you're going to be analyzing graphs of all sorts of functions and determining where certain quantities are positive and negative within different intervals is a big deal. And so drawing this little chart, this number line here, and then having space to decide whether something is positive or negative in between your markers is a good thing to have. Okay, so the final information for this problem has already been said, so I'll skip over it. Okay, so the next problem that I found that was kind of fun was from the pre-calculus subreddit. It was an exercise in using trig identities, but again, there's a secondary theme here that I want to emphasize. So the problem was to find this terrible looking value. This is really gross. Okay, but we can do it. So the first thing we want to do is just ignore this noise in the middle and just recognize that the bulk structure of this is that we're looking at the sine of one thing minus another thing. In other words, it looks like sine of a minus b. Now, yeah, the things that are playing the part of a and b are nasty, but you can ignore that for the moment. We're probably going to want to expand this using this identity. You certainly can't write this as just this sine of that inverse sine minus the sine of that inverse cosine. The sine function does not distribute, right? So we're probably going to want this trig identity. And then the interesting fact here, this sort of sub-theme for this problem, is to remember that if you're given the trig value of an angle and you know it as a ratio, then you're automatically going to know the other 5 trig values. You may have to dig for them a little bit, but you can find them with relatively little pain. So that's what I'm going to try to illustrate here. Okay, so here's the horrible part. Here is what this thing looks like when we expand it using the identity for sine of a minus b. So remember, a is the inverse sine term, capital B is the inverse cosine term. So this thing expands to the sine of a cosine of b. So the sine of the a thing times the cosine of the b thing, and then minus cosine a sine b, and that's what this is down here. So to evaluate the big expression, we need to evaluate 1, 2, 3, 4 clumps of trig functions. Now this one right here is pretty straightforward. It's the sine of the inverse sine of 7/25. Now, if you understand inverse functions and you understand that sine and inverse sine are inverses, thus the notation, you know that these two things essentially erase the effect of each other. So this should be 7/25. Just like the square root of something squared sends you back to the original number. The other way to think of it is to remember how to interpret this clump of notation right here. The inverse sine of 7/25 represents an angle. And we're saying, hey, angle, or hey, mystery angle, the sine of u is 7/25. So this is the angle whose sine is 7/25. And so this bigger blob is asking, what is the sine of the angle whose sine is 7/25? It's 7/25. Now, similarly, these terms here, the cosine and the inverse cosine, will eliminate each other, either through just inverse action or by understanding this inner quantity is asking for the angle whose cosine is -3/5. And so the whole thing is asking for the cosine of the angle whose cosine is -3/5. That's going to be -3/5. So there's 2 of the 4 numbers immediately. Now the second 2 blobs require a little bit more detail, and that's the fun part here. Right? Fun, my definition of fun might not be the same as yours, but this is what I wanted to stress here. The idea that if this inverse sine of 7/25, it is an angle. And even if we don't know what that angle is, we have enough information to discover the cosine of that angle, the tangent of that angle, and any of the other trig functions. And it's all about triangles. Okay, whoops, gave it away too soon. So let's say that this angle whose sine is 7/25, we'll just call it alpha, and I'm going to draw it into a triangle. Okay, since alpha is the angle whose sine is 7/25, and we know that sine is opposite edge over hypotenuse lengthwise, we know that we can put a 7 on this leg and a 25 on the hypotenuse, and now the sine of that angle is 7/25. If we know two legs of a right triangle, we can certainly find the other one by the Pythagorean theorem. So this lower edge has a length of, Pythagorean theorem says, square root of 25 squared minus 7 squared, which turns out to be 24. Okay, and this whole blob is saying, what is the cosine of the angle whose sine is 7/25? Now we know that cosine. It's 24/25. We could also give the tangent. It would be 7/24. We could give the secant. It would be 25/24, etc., etc. Now the other one, switch pages, and let's use blue. I'm tired of looking at red. Looks like I'm grading something. Okay, so the same story here with an added twist. This angle that's in the brackets, inverse cosine of -3/5, we'll call it beta. Beta is the angle whose cosine is -3/5. Or more precisely, beta is the angle whose reference angle is -3/5. Now, just based on the 3/5, this angle, forget the minus sign for a second, we know ratios going on here. So we know this needs to be a 3, this needs to be a 5. And then, sorry, that's not a 5, that's a right triangle bracket. Either by running through the Pythagorean theorem or just remembering your special triangles, we then discovered that the length of that side is 4. So if this angle was just, or this value was +3/5, beta is the angle whose cosine would be 3/5. The sine of that angle would be 4/5. Now, I'm not going to circle this yet because there's still this negative sign issue. Now, again, beta, the angle whose cosine is -3/5, or better, the angle whose reference angle has a cosine of 3/5. Since the cosine is -3/5, we know that this angle has to land in this quadrant or in this quadrant, right? Hopefully remember the ASTC rule. All trig functions are positive in quadrant 1. The sine, and so also its reciprocal, is positive in quadrant 2. Tangent, cotangent in 3. Cosecant, secant, quadrant 4, right? That's the rule about what's positive where. So there's 2 quadrants where the cosine is negative. So this angle lives in quadrant 2 or quadrant 3. Now the trick is, since we're looking for the sine of that angle, right, up here the sine would be positive, but down here the sine would be negative. Which one do we pick? Well, the answer of that goes to a subtlety in inverse functions, where you may remember there's a whole bunch of stuff about domain and range, restricted domain and the range that goes with it. You see these charts in your books that have all the inverse trig functions and then these intervals, like the intervals for the domain and the range. What is that about? Well, that chart is there. Those restrictions are there specifically to avoid this problem of having to decide which one of these two to pick as our answer, because they can't both be the answer. The inverse cosine is known to drop its results in these 2 quadrants. Okay, which means that when we ask for the inverse cosine of -3/5, we don't care about this one. We're interested in this one. The range of the inverse cosine is from 0 to pi, so that puts us in these 2. And so now we know that that's the special angle that we're looking for, which means that positive 4/5 is the sine that we are looking for. So when that's all said and done, where's my other slide? There we go. So the cosine of inverse sine of 7/25, 24/25, sine of inverse cosine of negative 3/5 is positive 4/5. And when we put all those numbers together, the final result, this is a lot of junk, but the final result is negative 117 over 125. Okay, so again, the lesson here, apart from the subtleties of domain and range of inverse trig functions, is that if we happen to know the sine or cosine of an angle, we can use that ratio to build a little triangle and figure out all the other trig values as well, so that we can call on them as needed. And that's actually going to come into play here as well. So there's a jump in the video there because I realized I said something in an awkward way while I was getting started. So clip, cut, start over for this third problem. This one's coming from the Ask Math subreddit. We're looking at the derivative of an inverse trig function composition. So the inverse sine of 1 over 1 plus x squared. Now, generally speaking, you may remember through formula and by the chain rule that the derivative of the inverse sine of something is going to be 1 over the square root of 1 times that thing squared times the derivative of that inside function. Again, chain rule coupled with the basic definition of derivative of inverse sine of x. Okay, now in this problem we're going to have some choices to make. No matter how we do this problem, and I'm actually going to show you that is choice number 2, is how we actually do this. In either one, we're going to need the derivative of 1 over 1 plus x squared. So choice number 1, are we going to do that with the quotient rule or with the chain rule? You have a choice. Here's how they both go. You can decide which one would be better. Quotient rule, sing it with me now. Low d high minus high d low, all over the square of the bottom we go. You would never catch Mick Foley doing that, but it's okay today. It's Halloween. So here's the quotient rule. For 1 over 1 plus x squared, low, the denominator, times d high, the derivative of the constant 1 is 0. So here's low d high. Then minus high, the top function, the numerator, d low, the derivative of 1 plus x squared is 2x. So low d high minus high d low, all over the square of the bottom we go. Just take that denominator and square it and simplify. Okay, so there's the derivative of 1 over 1 plus x squared. The choice was, are we going to do it with the quotient rule like we just did it, or do you want to do it with the chain rule and avoid the quotient rule because maybe you don't like the quotient rule? In this case, it wasn't that bad, but suppose you like to avoid it. So there we rewrite 1 over 1 plus x squared as a composition of a power function with the polynomial 1 plus x squared, and then we kick in the chain rule. The chain rule says, or the derivative part for the power function says drop that exponent down and then take its interior and remove 1 from the exponent. The chain rule says whatever's in here, multiply by the derivative of that thing on the outside. So negative 1 times 1 plus x squared to the minus 2 times the derivative of 1 plus x squared, and we're back to that same function. So neither one of them were too bad, but again, there's choices to be made. Oops. Now, to do the derivative of the main function, choice 1 is to do it by brute force, which then involves the nasty chain rule derivative formula for the inverse sine function, especially when there's a composition. So remember back there on the front page, we're implementing this thing for the function as a whole. So 1 over square root of 1 minus the thing squared. The thing is 1 over 1 plus x squared times the derivative of that thing. So here we need the derivative of 1 over 1 plus x squared, which is why we did the work on the previous page. Here we need some simplification. Now this is just tedious algebra, so I've gotten a common denominator between these two terms and merged them together. I've put in the derivative of this item, 1 over 1 plus x squared, based on the work on the previous page. This 1 over the square root of a fraction. I can flip the fraction underneath. I can also expand and simplify what used to be this numerator right here. When I multiply this out, there's a 1, there's a 2x squared, and there's an x to the 4th, but then the 1 subtracts away. It becomes the denominator. You know how this goes. It's all the algebra. Let the square root do its thing, and then do some cancellation. All right, so this is the result for doing this derivative by brute force. This is gross, and it's very easy to make mistakes. Here's a more clever way to do it. In calculus, usually Calc 1, the first semester, you learn about something called implicit differentiation. And very often it's a headache when you're first learning it. But the fact is that if you're okay doing implicit differentiation, it actually can make some problems easier. So don't discount it as a method. All right. Here's how that would go. We're going to take this function, write it as y equals the inverse sine of 1 over 1 plus x squared. This expression means y is the angle whose sine is 1 over 1 plus x squared. So the sine of y is 1 over 1 plus x squared, or just apply the sine function to both sides. Either way, you end up with this. Now, we're going to take this expression and ask for its derivative with respect to x on both sides. The right side is just this derivative of 1 over 1 plus x squared that we already worked through. The left-hand side says derivative with respect to x of something that's written as a function of y. Well, the chain rule says just do it like you would the derivative of sine of x squared. It's the cosine of that thing times the derivative of that thing. Right? There's your implicit differentiation. Then we can solve for dy dx by dividing both sides by cosine, which then tells us we have a secant of y on the right-hand side. Okay, now we need to untangle this secant of y. But from that previous problem we did, remember that if we know the value of one trig function, we know the other 5. Y is the angle whose sine is 1 over 1 plus x squared. So we can draw a triangle. Here's the angle y. Its sine is 1 over 1 plus x squared, which means that we can calculate the length of this side like so. Okay, I'm going to do this kind of fast. I'm reading it off my page. Right, that simplifies to 2x squared plus x to the 4th. That also happened. That very same simplification had to be done when we did that long, nasty brute force calculation. When this shakes out, it's just x square root of 2 plus x squared with a little bit of factoring. Okay, so the secant of y is going to be, we'll see, cosine is adjacent over hypotenuse, so the secant is hypotenuse over adjacent. 1 plus x squared over x square root of 2 plus x squared. And when we plop that information back into our derivative expression, like so, we can see some cancellation about to happen, and guess what? Same result as before. I would say that doing it with implicit differentiation is a little bit cleaner than doing it by brute force, but you have to be comfortable with implicit differentiation. All right, so those were the 3 problems I wanted to look at to investigate some themes that kind of ran as the undercurrent to those. By the time I edit this and get it posted, it's going to be, well, I'll probably get it done tomorrow, so it still might be before Halloween. But anyway, I hope you have a good Halloween, or that you had a good Halloween if you're not watching this till after, and that you got lots of good candy.